Well, applause. Hi everyone, I'm from Southampton University in the UK, and I'm going to introduce a very small research project that me and four guys who are also in the audience here embarked on our undergrad degree. So one of my favourite creatures is ants. They're capable of incredible collaboration on some amazing projects. They can engineer just like we can. They're also possibly the only animal that has agriculture. There are leaf-cutting ants who farm their own fungus, which in fact only grows in ant colonies, and they use it for food. They're capable of self-assembling into complex structures. There's a species of driver ants who can cross the jungle by day, and then by night they form together and build a structure out of their own bodies. And there are details within that structure. It's not just an amorphous mass. But there's not a single ant there controlling the whole situation. It's just each ant has a simple set of rules that it follows and applies to the stimulus that it receives. And through that, the emergent behavior is really quite complex. The most interesting result of that is that the collaboration scales over millions of creatures in a way that maybe contrasts much of our engineering at the moment. So wouldn't it be cool if we could do this with robots? That's the drive of swarm robotics research at the moment. These are some research robotics platforms from around the world. The top two from MIT, James McClurkin's Swarm Robotics Lab. Very impressive. And I believe the one on the top left there is the world's biggest robotic swarm at the moment, with over 100 individuals. At the bottom, two from Germany, a very nice collaboration between the universities of Karlsruhe and Stuttgart. I hope my pronunciation doesn't offend you too much. The bottom left one, particularly interesting. It's on the millimeter scale. Unfortunately, that's the only photo I could get, but the top surface there, I think, is 3.5 millimeters long. So really an exciting project. But what really makes these projects interesting is when they scale to large numbers of individuals. And obviously that pretty much comes down to two things. How much do they cost? And can you actually maintain a swarm that large? If you just imagine, I'm sure some of you have got experience with maybe working with microcontrollers or any kind of debugging situation, really. You have to sort of do a lot of tweaks, and there's a sort of cycle of developing and then flashing the code onto the device and plugging things in, unplugging things. Can you imagine doing that 1,000 times over? And what about keeping all of those robots in good charge, and maybe also the mechanics might deteriorate over time? So I think really the answer to maintenance is to get the robots to do it themselves, and we'll talk about that a bit later. So here's our swarm robotics platform. It's the cheapest one in the world, I believe, possibly by a factor of 10. But we think we haven't sacrificed too much functionality. The main thing that makes it cheap is an almost complete lack of custom mechanical components. So everything on there is just a standard printed circuit board, components soldered straight on, including the motors, and that really keeps the costs very low. You can phone up a standard electronics manufacturing company, get a lot of materials and schematics, and they can fabricate these for you for small amounts of money. Incidentally, that's the unit cost for just 25 robots, so a small swarm is affordable just for the maybe the amateur or the very small research group. So at the heart of our swarm robotics system is an MSP430 microcontroller. Many of you may be familiar with these, particularly if you've attended some of the talks or workshops here. It's a 16 megahertz part. It has 16 kilobytes of code space and 512 bytes of RAM. And we think these are sort of a sensible amount of power, which keeps the hardware working and allows some abstraction from that, leaving a little bit of space for some pretty advanced behaviors, which is really the interesting research part for a lot of people. So you can see the robot can interact with the rest of the swarm through its infrared communication channels. There are 3 channels around the device. Sorry, they're 1 logical channel, but 3 directions so that you can talk in 360 degrees. And also it can interact with this environment through some sensors and transducers. So it has the motors, which I mentioned, to drive around with. 2 motors in differential drive, so it can steer and so on. Some indicator LEDs to communicate with humans. A photoreflective sensor looking down to measure the reflectivity of the floor. So maybe you could use it to find objectives or maybe even follow lines on the floor. And it has ambient light sensing as well for some rudimentary navigation, which I'll introduce later. So here's the drive system. I'm just going to move through each of these systems and give you a little overview of some of the tips and tricks we've used to keep the simplicity and keep the costs very low. This is the drive system. It uses motors which are typically used to vibrate mobile phones or pagers. They're very, very small and, most importantly, incredibly cheap, particularly because of the large surplus market due to the very quick turnaround times in bringing out new models of mobile phones. Lots of these end up in surplus. So you can pick them up for maybe $1 each. Many of you may have seen a H-bridge circuit comprised of 4 transistors, in this case MOSFETs, to drive a motor. 2 motors, but only 1.5 H-bridges instead of 2. So this saves us 2 components, and more importantly, 2 components worth of PCB space. And the only real functionality we lose as a result is that we can't simultaneously drive both motors in opposite directions. However, we can still turn on the spot by quickly modulating between each motor, drive the left one backwards, the right one forwards, and you'll spin in some direction. And that's fine. We don't even really lose any speed because we're already using pulse width modulation to slow down the motors a lot. We were surprised at how fast they drove when we first turned them on at full power. We were expecting them maybe to lumber along under the weight of the motors, these tiny little motors not really used for driving any mechanical load, but we had a lot of trouble keeping them on the table. We used quite an interesting communication scheme over our infrared LED and photodiode arrangement. It uses a modulation scheme, a frequency shift keying based modulation scheme. Digital data is represented by the frequency of the transmission, like a sort of carrier wave sort of scheme. And the advantage of this is that you can filter with a high-pass filter the communication part that you want to keep and lose the very low frequency information, which is, or not information, noise, essentially, due to ambient lighting. So it makes it somewhat resilient to infrared light, to any visible light from ambient sources. It's pretty much what your TV remote does. We have a rotation-based coding scheme. It's MFSK because there's multiple frequencies involved. There's 3 on the diagram here in the corners. The data is not carried in what frequency you're transmitting. It's carried in the changes between frequencies. So rotating through this coding scheme clockwise will transmit a series of 1s, and anti-clockwise a series of 0s, and so on. You can twiddle left and right to transmit data. The nice thing about this is that it means you don't have to time the interval between two symbols, which is very resource consuming on a microcontroller. Instead, you only have to notice when it's changed and in which direction, and that's a new bit. It also means that synchronization is very simple. You don't have to maintain a constant awareness of the communications channel. This scheme I've drawn here with 3 dimensions, but it can go up to much larger symbol sets to transmit data faster at the expense of being more error prone. So at compilation time, you can just give a command line switch and make that trade-off yourself, depending on what situation you may have. So because we use the infrared links primarily for behavioral research. It's very interesting to see how sort of very small local communication interactions, which are very simple and noisy, can sum to a macroscopic behavior over the swarm. This is what most research groups are aiming for in the swarm robotics research. But also it can help us save the maintenance problem. These MSP430s can program their own flash, so with a bootloader we can program the robots over infrared. And when two robots meet, they say, what version are you? Oh, I'm version 2, I'm version 1. Firmware is downloaded across the link, it brings the new robot up to speed. So hopefully you may only need to program 1 or 2, and the whole swarm is suddenly version 3. This itself can be used for some interesting behavioral studies. So there can be a block of code which is integral to the robots, the kind of low-level hardware stuff driving the motors and the communications links. And then the behavioral blocks can occupy a separate portion of flash, and they can be exchanged between the robots. So they can maybe teach a new robot a new behavior by downloading that piece of code across. And so by having a number of these slots which can occupy these, which these blocks can occupy, you can have a community of small sub-programs which occupy the swarm, and the total memory of the swarm is greater than the memory of each individual robot, because as long as one robot has the particular code slab for maybe some sort of behavior or maybe a motor test function or something, as long as it doesn't die out in the community, another robot can have a different set of things, and so the total storage is larger. The infrared communications was also a source of genuine emergent fault behavior in our swarm. We had a simple virus-based scenario where the robots would light a red LED most of the time, and then there'd be a sort of green infection that would come into the swarm and propagate, and it would be more virulent than the red and take over the swarm with greenness. But the CRC check in our communication scheme turned out not to be strong enough, and so a whole new orange virus propagated through the community that just took us completely by surprise. So since we have 3 photodiodes for communication, these 3 down the bottom, and are somewhat sensitive to ambient light, we can also use them as sensors. So when we're not communicating, we're measuring the ambient light in 3 directions and use that to get a sort of compass bearing towards the lamp or the brightest source of light in the room. And to make that robust, we have 2 different bias resistors for each photodiode. One that we use for a high sensitivity mode for ambient light measurement, and then one that's low sensitivity for the communication, which allows high resolution ambient light measurement without the communication being swamped by ambient light. You can also see the high pass filter there to keep those 2 realms separate. We have this floor sensing LED photodiode combination there, and we use that to detect food tokens on the floor. You can also see the battery in the middle there, which is a lithium-ion battery, maybe the sort of size that one would get in a Bluetooth headset or something, but maybe a little shorter and fatter. And it's 320 milliamp hours, which gives us about 1 to 1.5 hours of continual drive time, which also surprised us. That's also as a result of the motors being so much faster than we need. We need only power them for sort of average 50% of the time or something and bring the current right down. The robots have these antlers and skis out the front. The skis are to keep them off the ground and keep them sliding around, and the antlers, the pair act as a charging input to the robot, so they can drive onto a grounded pad and a powered rail and charge up. They have a lithium-ion charge controller on board, which does add to the cost, adds maybe 45 pence, which is a significant fraction of the robot's cost. But the real advantage we get is that we don't have to worry about the kind of power source we're giving the robots or how many there are. We just have to ensure that the power supply is big enough, it can supply enough current to 30 robots at once or whatever, and each robot will manage its own charge. No one will end up overcharged or ideally not undercharged if they get there in time. That's also an interesting source of behavioral stuff, because when the robots die, you can use the power, the robots need to continue to live, which gives them an objective more basic than any of the behavioral stuff on top, if you code it that way. So now I'm going to talk about actually building these things. It's a sort of example of mass production at home. 25 robots were built in a single day with 9 people. This is a student house, nothing advanced. We've got sat around our kitchen table there, washing up in the background, but don't look at that. And there are people here who have never soldered anything before. By the end of the day, it was a long day, but let's not let that put you off. These people were soldering sub-millimeter 0603 surface mount devices, T-SOP components with 0.4 millimeters between the legs, and reliably too. So we had a very cautious quality assurance procedure. We had one guy who would not give out the chips or the resistors or whatever for the next stage of your build until you've proven to him that the ones that you've soldered on last time are all there, and the board passes some basic tests at each of these important nodes through the construction process. And through that, we ended up with a good way to learn soldering, and believe it or not, 25 working robots after a bit of rework. I mentioned the surplus mobile phone motors, very cheap, but the downside is they come with the eccentric weights on them, which is kind of erratic if you use them to drive robots. So we built this jig to pull the rope, or push the motor through the hole in the weight and discard the weight, because it's virtually impossible to do it by hand, but this really sped things up. The wheels, unfortunately, are the only custom mechanical components. The only part that we couldn't find a commercial off-the-shelf part that we could use instead, maybe a rubber washer or whatever. We had a look, there's nothing out there. So we built a simple tool to essentially press them from rubber sheet, and we used this setup to create about 100 100 wheels in an hour or so, which is not too painful. And there's a little jig there at the bottom for punching a concentric hole in the middle to accept the motor. There's no sort of glue or anything involved, so nothing to gum up your motors. We also have a little programming jig, a little bed of nails here to test the important nodes in the circuit, because connectors are really expensive. So you don't want to use those. Just have some bare copper pads on the PCB and some spring-loaded test pins come down and make contact, and that's a hell of a lot cheaper. So we're going to demonstrate the system to you now. Hopefully it'll work nicely. I shall switch to the video source. I guess the AV guys aren't here anymore. Perhaps the camera's just powered itself off. Oh, excellent. Hi. Great. So, sorry I got to a bit late there, but you can see that in these 2/3 of the arena there are these little black and white food tokens. The objective is to push these to the lamp, which is at the very far end in the third of the arena. That was empty at the start, I promise. Now, the robots have no concept of navigation through this space, which is maybe evident. They do know when they've hit a wall because they know that their light bearing hasn't changed for a while. So then there's like a watchdog timer and they back out, do a little random spin and carry on. They do a random walk until they encounter a food token, like this one here. And then they'll endeavour to light seek using kind of Breitenberg-style behaviour. And they'll push tokens to the land. I'll invite my colleague Steve here just to tweak the ones which are stuck too horribly, but you know, I want them to do mostly their own thing. The good thing about having 25 robots is that 10 of them can not work very well, and you can still achieve great things. You can see the mood indicator LEDs on the top, and they're reflecting the internal state of the robot. There's red, yellow, and green. The red and yellow may be a little indistinguishable on the video. But they flash red when they're dangerously low on power. Then they're trying to avoid the light and get to the charger at the bottom here. So that guy just there, who was just flashing red, thought he was dangerously low on battery power, but has now found some food, and maybe that's more important to him. When the robots have a green LED, they think they've found food, and that engages the light-seeking behavior. They're also always communicating with each other. Whenever they're within a short distance, maybe about 5 to 10 centimeters, they can communicate, and they're asking, or they're transmitting, I last saw food N seconds ago. So this enables the whole community, they average their value with that they've received from everyone else. So through the community, there's a kind of average how much food is there left value, which will gradually drop as all of the food migrates up to the other end. And when the robots all decide that there's not much food left, they'll start flashing green and driving home. That's when they haven't seen food for 30 seconds, or the average of their value with someone else's is under that time. So you can get involved with the Swarm Robots projects, the Formica Robotics adventure. They're very, very cheap, as I say, and they're available in the Creative Commons license for the hardware and GPL for the software. You can download them from some URLs, which I'll put up at the end. We would like that. Let's say, if anyone's interested in getting into MSP 430s, this is a great little development board, because most development boards you buy come with some LEDs and some switches and stuff, which is kind of cool. But these ones can drive around. So I definitely recommend them. There's the excellent open, or almost open toolchain available for development under Linux. The MSP GCC toolchain. Some of the other talks here have been mentioning that set of software, so I'd recommend it for any of you hardware freaks. This one is probably missing a wheel. That's a common failure mode. Yeah? Yeah. There are some spares, I think, in the box down here, perhaps. So, I think that pretty much concludes the demo. Everyone flashing here has decided that there's no more food left. A good sort of third of the food is at the far end, which, you know, ain't bad. And these guys are trying to charge. You see he's losing contact there every now and again. If they can test when they're in contact with the charger, and if you disturb them, they'll back up and try again. So try and hold that one away with your finger, Steve. Yeah, just put your finger in front of him. You see him drive forwards there. And he gets really angry after a while. You're right in front. This is my first talk, so occasional blunders. So I guess we can take some questions, if anyone's interested.
Is this mic on? Yeah, okay. Question, there were units that seemed to behave better than others, got more work done. Were the programs were all the same? What accounts for the difference? Just random chance?
Yeah, that's a good question. There are several factors involved, some mechanical, and an electronic one is battery status. If they're very, very low on power, then they tend not to behave quite so well. Also, the mechanical factors, such as the metal prongs at the front, they sometimes get bent and introduce some new steering characteristics. And some of the ones charging there may lose contact more often than others because of these sort of mechanical problems. So all of these things sum to change the behavior, and it's exactly those kind of effects that are exciting in swarm robotics research. Another question, perhaps? Does that answer your question?
Yes.
Good.
What are all the differences between doing these things in hardware and between simulating them in software?
I'm glad that question came up because I forgot to mention that. There are swarm robotics researchers who do a lot of simulations, and there are a few who do a lot of hardware stuff as well. The simulations are obviously a very powerful tool to explore these phenomena, but there are new phenomena that arise just as a result of doing it from hardware, which are also interesting. So if you're building a model in software of your robots, you can't possibly think of all of the things it can do. Can't stress that enough. So doing it in hardware teaches some new tricks. Secondly, although these are mostly still used in research, they're just beginning to come into practical applications, and so the pragmatic hardware stuff really becomes important. You can no longer ignore sort of current consumption or any of those factors. Another question, maybe? So you can see they're all quite happily charging there. Can we? You can't actually see them. Maybe we can pan the camera down slightly. But some of you who can see the orange flashing lights there, they're happy robots charging. Okay.
Okay. In addition to the virus experiment, did you try to do some artificial evolution on the robots?
No, that would be fascinating to do. We've tried a few behavioural scenarios, but none have involved different bits of code floating through the community yet, and I'd really like to try that sometime. Unfortunately, there isn't a kit available at the moment. The question was, where can we buy a kit, by the way, since he wasn't on the microphone. We may make one available if demand is high. Yes. Maybe we can change back to the slide.
How long does it take for one robot to transmit its new software to another?
Good question. I don't know the precise number, but to completely download code across the link probably takes in the order of 10 seconds or... Yeah. Okay, my colleague who worked on that particular part of the firmware said that it might take up to a few minutes, but they don't transmit it all in one session. So as robots drive past each other, they'll transmit small blocks of firmware until a whole picture has built up, which is bootable, and then they'll sort of do a pivot route style switchover and boot the new firmware. So it's quite robust to not collecting all the data fast enough. Yes, we get a microphone maybe?
I have a question. How do they find the...
Sorry, I was just taking a question from the guy without a microphone. Okay, yes, carry on.
How long does it take for a new firmware update to propagate throughout the whole swarm?
The question was, how long does it take for a new firmware upgrade to completely propagate through the swarm? The answer yet is that it's untested. But, thank you. I would estimate, well, it's one of those exponential things, isn't it? Because if you just introduce one new robot with the firmware, he has to give it to one other, and then you've got two transmitting to four, and so on. So each of those times maybe a few minutes, and so do the exponential over the population until that tends to something. But I don't know what that answer is precisely. I should just switch right to the end. Yeah, at the end. So in answer to the kit, the full design materials are available here, including a bill of materials and the PCB layouts, the schematics, the firmware, everything you need except the PCB. But maybe if demand is high, we might consider making a kit. I don't know. It's pretty experimental, but I'd like to try it. So yeah, software at xscape.com/Formica and hardware at warrantyvoidifremoved.com/Formica.
Okay. How do they find the charging station?
In this scenario, they're avoiding the lamp. So the lamp is at this end here. They drive towards the lamp to deliver food and then away from it to find the charger. That's what they're capable of at the moment, navigation-wise.
Have you talked about maybe sending an infrared signal to find the loading or charging station?
We haven't tried that. It certainly may be possible, but you need to know your range away from the charger.
Yeah, maybe
I guess you can look at the power dropping off, maybe, yeah.
Maybe the robots can propagate who can see the charging station.
Sorry, say that one more time?
Maybe the robots can communicate where the charging station is. Yeah.
I'm sorry, yes. Maybe the robots could communicate where the charger is. Yes, they could also do that. So maybe you have a counter which resets when they're at the charger, and then they transfer that information on to other robots, and that would decay with time so that the robots who interact with near the charger know that the charger is nearby. That would probably work, and just from the audience questions, I can see that there's a lot of behaviors that we could try out. And in the 10 weeks of the project, we tried only a tiny, tiny subset. So it would be great to take it further. Yes, at the front here.
Do you already know what the lifetime of the motor is?
Until they stop functioning?
Yes.
What other kind of lifetime is there? Who knows? I suppose mostly that would be limited by the battery. Lithium-ion batteries, as anyone who's owned a recent laptop will know, tend to stop working after a couple of years. So there's that factor. The motor, the wheels wear down somewhat as well. The loss becomes really apparent in these small wheels. So we haven't yet changed the wheels, but there are some robots with them running very low after maybe a day of drive time or something. So yeah, that's an issue. Mechanically though, they're very, very robust, and we haven't had any motors burning out or anything. So those are the two big factors, I would say. Okay, are we out of time, or any more out of questions, perhaps?
We still have time.
Okay. Can anyone think of anything? Have I missed anything, team?
What about collaborative behavior?
Sorry?
What about collaborative behavior?
Calibrate.
Collaborative behavior?
Collaborative behavior. Yes, that's the absolute drive of all of this. This is a basic collaborative task here where they have a hive perception, and we've demonstrated that that works. We've also published, we have an abstract published about a demonstration we gave at the Artificial Life Conference in Winchester a few months ago that demonstrated a task distribution algorithm through the community. So where this was kind of inspired by ants. So ants may be foraging, tidying the nest, or raising young. And the number of ants in the community that are devoted to each of these tasks is adaptive. And we showed an algorithm working on the robots that emulated that sort of behavior in a completely decentralized way. And the interesting thing about this algorithm was that the tasks were a one-time only thing, and the ants would forget a task if another ant hadn't told them about it. And so the challenge was to maintain all of these tasks swimming around in the population without them dying out, and it worked quite nicely. Future improvements to the platform. Excellent question. The mechanics need a little bit of improvement. As you can see, the wheels sometimes fall off. The metal prongs change shape and impede their charging. Also, yeah, radio would be really nice to add, because debugging them is something that is really painful to do at the moment. And so if they could transmit their status between each other and back to the humans in a more wideband, longer range thing than just infrared, that would be great. We're looking at maybe the MSP 430 and ChipCon radio fusion for that's coming out soon. Yes?
Have you so far performed any comparison between simulations?
Would you like to repeat?
Have you so far performed any comparison of simulation of the swarm behavior and the actual behavior?
Yes. In the work published in the Artificial Life Conference, the task distribution algorithm, we did show a correlation between simulation and reality, which was, a relief. That worked quite nicely. We are working on a paper that will contain this data that you can read for yourselves, but it's not out yet, so details will be posted on those links. Okay. Well, if there's no more, I guess we'll wrap it up there. These are my other interests. If anyone fancies talking to me during the conference about any of these, that would be great. But otherwise, thank you and goodbye.